All right, I think it's time to get started again. Very happy to have Beatrix Muehlmann, who's going to give the next talk on DS2 in Timelike super Liouville theory. Take it away.
Okay, good. Yes, it works. Okay, so thanks a lot for this invitation. It's cool to be here. I hadn't realized how much I missed being home, Italy. So except for the mosquitoes, I hate them. So okay, so I'll be talking about some ongoing work on trying to understand, trying to explore two-dimensional de Sitter space. And I'm coming from a completely Euclidean perspective here. So I'm approaching the problem in a very Euclidean sense. So this is all based on two papers in particular that we wrote with Dionysios Aninos and Teresa Bautista, and on some ongoing work with Aninos and Pietro Benetti Giannolini. Very good. So as I mentioned, like I'm interested in two-dimensional de Sitter space. For the sake of not losing completely contact with our real world, I still drew the Penrose diagram of four-dimensional de Sitter space. So, but actually, let me start here. So, I mean, we have this measurement. So we have these observations that from like CMB, supernova, and like LSS, and so on and so forth, right? That we have been entered this stage of accelerated expansion. So, we believe that this expansion is driven by a positive cosmological constant. So, like asymptotically, we're going to live in a de Sitter universe. And the consequences of living in such a space-time that's exponentially expanding is basically that if you're a little observer in this space-time, there's going to be eventually a cosmological horizon that's surrounding you. It arises essentially because of the fact that at some point, light will not be able to reach you anymore because the expansion of space-time is just so fast. And just to give you exactly like this some data here, so and I'm not an experimentalist, but still like giving you some data because I think it's really cool. So of the measurements of the cosmological constant, we infer that this cosmological horizon is a distance of around 20 billion light years away at the moment. So that's our universe. That's what we can see. Beyond this, we cannot see. And so there's this cosmological horizon. You also really draw, oops, if you draw the Penrose diagram of de Sitter space. So the Penrose diagram of global de Sitter is this square. So it's the square over there. But we can actually not see all of this. What we can see is this little triangle over here. So this is the static patch. And here, this green line over here is basically reflecting this horizon that's surrounding us. So we are this little observer moving up here, and we have this horizon that's surrounding us. Very good. So now what you're all used to, I guess, is like this hyperboloid representation of de Sitter space. But for the sake of my talk, what I'm really interested in, as I mentioned before, is Euclidean signature. So you might wonder, what happens if I take like a global patch of de Sitter space or a static patch of de Sitter space and rotate that? And it turns out that rotating both the global patch and the static patch for de Sitter space to Euclidean signature, you're going to get this sphere. So this sphere is the representation of d-dimensional de Sitter space. So the D sphere is the representation of d-dimensional de Sitter space. So like, don't get these two spheres wrong, right? I mean, this is the representation, the Euclidean representation of de Sitter space. This is this codimension 2 horizon, like so. But anyhow, so and now what we have seen that we have this cosmological horizon that's surrounding us, and now very much inspired by black holes. What we've done is that we have associated an entropy to this horizon. So we are saying, oh, look, this horizon has a certain area. And now we are saying, oh, well, let's be inspired. Let's assume that the entropy of the Sitter space is given by the area of this cosmological horizon divided by 4G. And plugging in like this radius here, we're going to find an entropy that's of order 10 to the 120. Or another way, like this would predict that we have afforded 10 to the 120 microstates. And so like one of the motivations for my work is that we have no microscopic theory for this 10 to the 10 to the 120 microstates. And so one idea for me is that to try to understand models that could maybe give us hints of what these microstates are. But let's start microscopically here. So this is also like, this is like a formula inspired by black holes. There's also a, if you want to say it, like a conjecture that's coming from Gibbons and Hawking. And Gibbons and Hawking were conjecturing that the Sitter entropy is encoded in the gravitational Euclidean path integral. So you take a Euclidean path integral, and so this gravitational path integral with the boundary condition that there are no boundaries. So you're summing over all compact manifolds, and then you consider this object here. Okay, so you consider this Euclidean gravitational path integral, where, as I said before, we are summing over compact manifolds, and as E is the Euclidean Einstein-Hilbert action, we have a positive cosmological constant, we're interested in the sitter, and I allowed myself some matter. Now, if you want, like, I mean, I think this is like what demystifies this proposal a lot is like, take, for example, like for the 4-dimensional Einstein-Hilbert action with positive cosmological constant. If you then evaluate this object on the sphere saddle, you will exactly get e to the power of area over 4G. So this really like kind of demystifies this Gibbons and Hawking conjecture and ties it to this equation over here that we very naively wrote down. But still, this is like the leading saddle. So you might really wonder, like, what is this gravitational path integral? In general, like, we cannot really solve this. So we cannot really go to a higher order. So one of the ideas that we've been pursuing over the last couple of years is that we've been trying to basically lower the dimension as much as possible, being also like inspired by the fact that we have gained so much from like ADS2, from like general 2-dimensional theories, and try to understand the 2-dimensional sitter setup in, so basically Euclidean gravitational path integral in DS2. Very good. So what is this gravitational path integral in 2 dimensions? So if you take this object over here and go to 2 dimensions, so we all very well know that in 2 dimensions, our metric has 3 degrees of freedom. It's a 2 times 2 matrix, it's symmetric. So we gauge the diffeomorphism, and then what we can do is that we can write the metric in Weil gauge. So we can gauge the diffeomorphism, and we are left with 1 degree of freedom, which is known as the Weil mode. And so this is this bar phi over here. Now this metric G tilde over here, it's, I think in the in the older literature, it's called the Fiducial Metric. It's a metric that once you fix a topology, it's fixed. There's nothing that you can do with it anymore. But the real honest to God physical thing is Gij. So this is just a fixed background metric that you fixed for a given topology once and for all. But then what you can see here, so we started with an integral that whose measure was over all matrix G. Now what's fluctuating is phi. So we want to change the measure from G to phi. And what we know is if you change the measure from G from one variable to another variable, that's going to be a Jacobian. And as it has been conjectured in the 80s already by Dissler, David, and Kawai, is that the resulting Jacobian is what's known as Liouville, the Liouville theory. So in 2 dimensions, this gravitational path integral is the following object. I'll explain the notation in a second. Okay, very good. Let me explain the notation. So the notation, let's start from left to right. So first of all, I was a bit cheating before already, because I told you guys that we are summing of all compact manifolds, but it's not totally clear what are compact manifolds actually in arbitrary dimension. But in 2 dimensions, we're also saved, because in 2 dimensions, we have a very clear understanding what are compact manifolds. So, and these compact manifolds or these manifolds that have a specific genus H. So we have a sphere, we have a torus, and so on and so forth. And so basically chi-H here is the Euler characteristic for these surfaces. And theta over here for me is a coupling of the Euler characteristic. That of course arises because in 2 dimensions, like the Ricci scalar is topological, so it gives you this Euler characteristic. And then, as I mentioned before, so I changed the measure to phi. I have this Liouville action over here, which I'll write down in just a second. For the sake of my talk, I've been assuming that the matter theory here is a 2-dimensional CFT. And because I went to Weyl gauge, I have some BC ghosts. Now, as promised, the Liouville action is given by the following form. So as said before, right, the only thing that I have left here is G tilde. So, and then I have a kinetic term. Okay, very good. So I have this action over here, this Liouville type action, which has this exponential interaction here. R tilde is the Ricci scalar associated with this metric G tilde. And Q and B, these are 2 parameters of Liouville theory that are set in such a way that Liouville theory is a 2-dimensional CFT. So we have that the Liouville central charge is 1 plus 6Q squared. The Q is equal to B plus B inverse. So this is set in such a way that we have this 2-dimensional CFT. And now, to avoid the appearance of a conformal anomaly in 2 dimensions, what we have is that we have this constraint that the central charge of the matter theory plus the central charge of Liouville plus the central charge of the BC ghost adds up to 0. And because it will help me in just a second, let me also write down what this implies for Q and B. So it implies for Q and B that they obey the following constraint. Okay, so it implies that Q and B obey the following constraint. This will just be useful in just a second. So in principle, I started with the Gibbons-Hawking conjecture, and I told you that I want to try and examine this in 2 dimensions. Now, what we have here is that we want to have in this gravitational path integral over here, we want to have a leading saddle, which is a sphere. So that should be the leading contributions. However, now you take the Liouville action here. If you fix, say, really just at 0, so just the sphere here, then you can go ahead and calculate the equations of motion of this theory, and it will tell you that there is not one single real valued saddle. So you have not a single real valued sphere saddle. So, so basically you might think, okay, now that's it, end of the story. Like I try to set up something and I'm running against the wall. There is no sphere saddle. Like how would you at the leading order I fail? However, what's going to save you is essentially these 2 equations here. Because what you can see from these 2 equations is the following. So depending on what C matter is, Q and B are going to be real or imaginary. So in particular, there's this one regime for which C matter is bigger than 25, in which both Q and B are real. And sorry, both Q and B are imaginary. So Q and B are purely imaginary here. So let me just point this out without hoping not to confuse you. I mean, the regime that's very well studied that we have explored with like the matrix model duality is the regime where C matter is less or equal to 1. So that's the regime which is very well explored, where we have the matrix model dual and so on and so forth. This regime C matter bigger than 25 hasn't been explored too much in the literature. And if you know that, of course, like you also see that there's a regime between 25 and 1, which is not explored at all. So we have no idea about this regime at all. Why is that the case? This is the case because in C matter bigger than 25, both Q and B are imaginary. Whereas if you're between 1 and 25, only B is imaginary. And here, if both Q and B are imaginary, then you can save yourself again. You can take this action over here and do this following rotation. So you take also the Weyl factor phi, and Q and B, and you ubiquitate all of them. So you end up with this new parameters. So you end up with new parameters phi, Q, and beta. And in terms of these variables, you're getting the following action. So you're getting the action which is known as time-like Liouville theory. Note that time-like is not Lorentzian. I'm still in Euclidean signature. This is just a name. So it's this action, which importantly, and this is what gives it its name, it has this wrong kinetic term, which however is not even something that we are not used to, right? I mean, this is what we know from the Euclidean gravitational path integral in general. That's why Gibbons, Hawking, and Perry started recrotating things. So, but what's very important here is this sign here, and you will see this in a second. And let me just I guess you've already seen this, but because I recrotated all of those variables, I went back to a real valued action. So this thing over here is again real valued, which is essentially what you cannot achieve in the regime where symmetry is between 1 and 25. So that's why we have a manifestly complex action in this regime and don't touch it. But in this regime where symmetry is bigger than 25, we have a real valued action. And very importantly, and even though these colored chalks are not great, let me highlight this thing here. So what you can see as compared to this action over there, there's an opposite sign between this linear term in phi and this exponential term. And this is what saves you. Because what do we want? Let me just repeat what we want, because maybe I haven't highlighted it enough. We are, at least if we are in the sphere, where we have a positive Ricci scalar, we want to have a sphere saddle. So on the sphere, we might have fixed G tilde. We might have fixed the topology to be a sphere. But as I have told you above, what's physical, what gives us the geometry is G and not G tilde. So unless phi collapses under something constant and is not fluctuating, we have no saddle. But essentially, because of this change of sign here, if you now calculate the equations of motion of this theory, you do find a constant real valued saddle. So we find a saddle phi star, which is constant. And this is important because now we won. So basically now we have constructed a theory of two-dimensional quantum gravity, which has a two-dimensional de Sitter saddle. Very good. Now let me, I hope this is clear. So let me try to explain you some more details, some more things about time-like Liouville theory now. So time-like Liouville theory is as its sibling space-like Liouville theory over there, conjectured to be a two-dimensional CFT. However, it is a non-unitary two-dimensional CFT. So it has negative central charge that's given by this equation over here. And very good. But other than that, it's a nicely behaved theory. And if you let me split off just the gravity part in this gravitational path integral over here, we are interested in the sphere partition function now of this object. So this is really just the gravity part in this gravitational path integral over there. And what I did here is that I modeled out the residual gauge transformations on the sphere. So even if I fix Val gauge, I still am left with Möbius transformations on the sphere. And okay, now what I did is that I just told you that this action over here has a sphere saddle. This is good. But actually even more happens. And I spare you all the details, even though if I'm happy to explain you all the details. What you can do is that you can say, oh, now let me take my phi, and let me say it's a phi star plus a small fluctuation. And let me not just be happy with calculating the leading saddle of this gravitational path integral, but let me get crazy and calculate loop corrections. This isn't done all really hard. In this setup, we can do this order by order by order by order. So you can go to 2 loop, you can go to 3 loop. If you have really good students, you can force them to go to 4 loop. And you can calculate this order by order, which is really cool, I think. And all the UV divergences cancel out. And this is a perfectly well-behaved sphere partition function that you can calculate. And what happens basically, what you find if you calculate this order by order in these fluctuations is that you find, I mean, it's a sphere partition function, right? So the first thing that we want to find is the sphere anomaly. So say the area of my two spheres upsilon. So then the first thing that, of course, I want to find is the anomaly, which is like C/6. Check, this is the first thing that I wanted. Then I have some lambda to some power and some UV cutoff to some power. Of course, such that these powers all make this thing dimensionless. And then I have this expansion in this parameter beta. I think I was sloppy here and didn't highlight something, which I will do in just a second. So I haven't highlighted this. I hope maybe you inferred this already, but in 2 dimensions, we don't have a Newton's constant, right? So what is ordering, what is giving us a semi-classical theory here? In 2 dimensions, what's giving us a semi-classical limit is the limit in which beta is going to 0. So in which this parameter there is going to 0. And what you can infer, of course, also like from this constraints over there, is that beta going to 0 is equivalent to sending b to infinity, or also sending for example, the matter central charge to plus infinity in this setup. Very good. So we have this order by order expansion of this gravitational path integral that we can do. So we can perform like the 2 loops, we can perform the 3 loops, and this is great. You can all do this. So for example, like let me just highlight this here. So this coefficient C2, it's made up of a bunch of diagrams, and I think they all look like, so they look like, let me see. I drew them because I knew that I forgot them. Which one did I forget? Exactly. So this C2 coefficient is made up of a bunch of diagrams, and in principle, what's left is 4 diagrams. But this is not all that I had, right? So in the beginning, this 3-loop contribution over here, it was made up of like 40 diagrams or so. But out of some magic, all of those like 26 diagrams canceled. Sorry, 36 diagrams, all of them canceled. And let me just highlight that it's not just like UV divergences that canceled, it's also finite contributions that canceled. But all of those canceled to make up a coefficient C2. And now, yes, go ahead. Say what?
So those diagrams are computed in a carved background or not?
In a what background?
Curved background.
Oh, yeah, exactly. They're on the sphere.
On the sphere, right?
On the 2 sphere, yeah.
Which regularization do you use for coincident point?
I mean, what do you mean? I mean, there's all the UV divergences, they just cancel each other out. There's nothing that you need to regularize.
No,
they just go away.
If you have a 3 vertex, then you can construct the tadpole.
Yeah, but I mean, we have a tadpole, but it cancels out with some cactus.
Independently on the regularization.
Yeah.
But in a curved space, you can regularize in different ways.
But I don't even need to regularize. I mean, if I have a diagram, as you were saying, I mean, I have some tadpole.
Yeah,
exactly. So that's what happens here. So at 2-loop order, I have a tadpole, I have a cactus, and I have a melon.
Yeah, only the second one is divergent.
No, the cactus is divergent as well.
Yeah, the third one, right?
Yeah.
The 2 of them cancel.
The 2 of them cancel on the nose. There's nothing that you need to do. There's no divergence scheme that I mean, it's not like that just the UV divergence is canceled. The whole diagrams cancel. Because of the setup of this theory, these 2 diagrams, all of it cancels on the nose. And the same thing happens
also the finite parts.
Yeah, also the finite part.
Thank you.
Everything cancels. That's really remarkable, I think. That it's not just that you don't need to introduce a regularization scheme or anything.
But this is not true in the other regime, right? The regime 1.
No.
Also in that regime.
You mean here, right? Like no.
Real B.
It's not the case. No. This is just Timelike. This just happens.
Only
here.
time. Oh, so it's a magic of time regime. Okay, thank you.
It's black magic. There's something happening here, yes, which I think is very interesting. But I think what's more interesting now is that, okay, I mean, I have to admit I only calculated this to 3-loop, So it's not that I magically inferred that you would have calculated this forward and forward and forward to 4 loop, 5 loop, 6 loop, and so on and so forth. But what's true is that you can actually resum this. So this is not an asymptotic series. This is a series that can be resummed. So so basically what you infer, and this is not coming from the gravitational path integral now. This is coming from the fact that Liouville theory is a CFT. So you use CFT data here, and then you do infer that this whole series over here that you get can be resummed. And what it is a ratio of gamma functions. It's a simple function, and this simple function is a ratio of gamma functions. So I think this is very remarkable. So the fact that your whole gravitational path integral over here turns out to be nothing else than a function. A simple function of gamma, a simple function which is a ratio of gamma functions. So something like gamma of 1 plus beta squared over something like easy. It is not important for the sake of this talk now, so I don't write it down. But this collapse of a gravitational path integral onto a number, I think is very interesting. Very good. So, and it will be the first hint or the first curiosity that will make us consider a very strong machinery, which is supersymmetry, to try and understand what is the reason behind this. As you were inferring, as you were asking before, right? Have this on the nose cancellation of diagrams of finite part and divergent part. And so it's interesting what is forcing this calculation, like what symmetry is making, giving us all those cancellations and forcing a gravitational path integral to collapse onto a number. And let me also give a second hint for why we should consider this strong machinery of supersymmetry. The second hint, let me write this down over there. Sorry, spare one blackboard. Is the following thing. So I was a bit cheaty, sorry, I mean, not cheaty, but I was just explaining you like the leading contribution. So I was just explaining you the sphere. So I didn't give you any other details. So for any other topologies. So what you can consider, of course, is like higher genus contributions and so on and so forth. So you might wonder, like, are these allowed? I mean, in principle, why should we not include them? I mean, in the Gibbons-Hawking conjecture, they told us to sum of all metrics. So why not summing of all topologies? So in principle, I should not just stop at the sphere, but I should in principle go on and consider like higher topologies. But I really want to emphasize this though. I don't have boundaries, right? I have compact manifolds. I have no boundaries. So I'm considering like this time-lapse theory coupled to a matter CFT on compact higher genus surfaces. However, we're running into trouble. So on higher genus, on higher genus surfaces, we run into trouble because essentially like the matter theory, which I perfectly well erased just now. So the matter theory, at least in the semi-classical limit, which just re-emphasizes the limit where the matter central charge is very large, we have this behavior like, which is roughly of this form here, right? So Alex is not here, so no one is going to be grumpy that I don't get the right coefficients here. So, but if I have like, if I couple this to gravity, I have to integrate over the whole fundamental domain. So I'm gonna get a UV divergence. So I'm gonna get this divergence, which is associated with the high temperature limit. But for example, like on the torus, that's the limit in which like I have this trace of e to the power of minus beta h and take beta to 0. So it's to some extent we can interpret this also as a divergence that's associated to the infinite dimensionality of the CFT Hilbert space. So I have this divergence at higher genera. At higher genera. That's sensitive to the dimensionality of Hilbert space. So basically, I have two problems. Even though time-like Liouville theory seems to be an incredibly interesting theory that gives me like two-dimensional de Sitter on this sphere, and I can calculate the separation function to all orders. It collapses under a ratio of gamma functions. It has some problems on higher genera. However, these are two hints now. These are two curiosities. These are two things that I found. I first found the collapse onto a function. And second, I found divergences that are tied to the fact that I have an infinite dimensional Hilbert space. So for us, and like these two things were hints to consider something else, to consider like something that might teach us something of what can we do. And this what for us at this stage was supersymmetry. So we were like, look, there's at least one machinery where we can understand this localization very well. So at least if you want to call this thing, this collapse of a gravitational path integral on the ratio of gamma functions, a localization. And this one machinery that has taught us a lot about this localization is supersymmetry. So we have supersymmetric localization. And the second thing is that we encountered a divergence associated to an infinite dimensional Hilbert space. One thing that supersymmetry does is that it adds a lot of cancellations. So maybe at higher genera, there's enough cancellations to give us a setup where we can even study higher genera. So this is what made us introduce this theory, which as far as I know, has really not been introduced in the literature, which is what we call Encoded 2 time-like super Liouville theory. So it is a theory that has Encoded 2 supersymmetry, and it is basically the extension of time-like Liouville theory. So like basically it's in this Encoded 2 theory, we have a chiral and an anti-chiral multiplet. And because I'm very pedantic, I'm putting tildes on my anti-chiral multiplet. Why am I doing this? So I'm just explaining you this because I also had to learn supersymmetry from scratch. So maybe some of you know this. I did not know this before I learned this stuff. It's Euclidean signature. My phi tilde is not necessarily phi dagger. So as long as I'm in Euclidean signature, I cannot tell that phi tilde is phi dagger. This is something that I can do in Lorentzian signature. As long as I'm sticking to Euclidean signature, I cannot do this. So that's why I'm putting this tildes to my anti-chiral multiplet here. But then in the end, what I have is a complex scalar phi, a Dirac fermion psi, and some auxiliary field f. Where of course the counting works out, right? I have like 2 + 2 and 4, so all fine. And then this action, or let me only write down the Lagrangian of super time-like Liouville theory, is given by this expression. So I have a wrong sign kinetic term for my scalar field. I have a linear term. Let me write down our tilde. So I have the border part of this linear term over there. Okay, I will mention in a second why I have beta here. And then I have, well, the term associated to the auxiliary field f. I mean, I'm off shell here, so I haven't integrated out anything yet. Then I have kinetic term for the fermions. And then I have my superpotential. Sorry, I wanted to write this down beforehand, but I mean, black parts cannot hide each other, so I didn't want it to like not surprise you with this. Okay, so I have this Lagrangian over here, which we introduced to be a theory, which is basically time-like Liouville theory. So it has this wrong sign here, minus gij tilde, and minus for the linear term. And I have a superpotential W, which I choose to be of exponential form because I want to mimic Liouville theory. with phi tilde. So just to touch base again with this lambda over here. So in this setup, if we define, if you plug in W and W tilde here and integrate out F, so go on shell, you will really get a bosonic action that looks like the first line over there. And then you can define the cosmological constant to be this combination over here. And in particular, it is positive. So what this theory is going to give you, it's going to give you a de Sitter saddle. It's going to give you a two-dimensional sphere saddle. So basically, we found a theory that's supersymmetric and has de Sitter. And now you might yell at me and be like, no, I cannot have Susi and de Sitter. So in general, like this does not like each other. But saving us here is the fact that our theory is still non-unitary. So I have a non-unitary theory that I combine with de Sitter and supersymmetry. And at least at this stage, we have not found any flaws. So at this stage, nothing was shouting into our face and telling us, no, I still don't like Susi. So de Sitter at this stage is still happy with the fact that we have allowed it to be non-unitary, and it's not doing anything to us at this stage. But let me also highlight that this is work in progress. But still, this theory over here, it admits this DS2 saddle. So basically, what I can do is that I can study this Euclidean gravitational path integral of this supersymmetric theory of time-like Liouville theory. So I can study this gravitational path integral. Time-like Liouville theory. So before telling you the punchline of what happens with this gravitational path integral, okay, no, you can ask me more details if you want to have more details on this setup of this action, like you want R charge and so on and so forth. Please feel free to ask me that later. But I'm not sure how much it will bring us if I enter these details now, even though I think it's remarkably interesting. But let me tell you the punchline of what happens to this gravitational path integral. So this is the gravitational path integral I should highlight for now on this sphere. So I motivated introducing supersymmetry with this localization argument over there. So you might wonder, does this theory localize? Can I take this theory over there and localize it? And the answer to this question is yes. And the answer to this question is even stronger. The answer to this question is that this full action over here, so the action associated to this Lagrangian is Q exact. So I cannot just localize it. Naively, supersymmetric localization would tell me that this whole thing, which by what I just said, is some Q exact term. So this whole action over here is just the supersymmetric, is just a Q exact term. So Q is a supercharge. So this whole thing I can write in this way. And then Susi localization would tell us that this whole thing in a normalization that you can choose is just 0. So Susi localization would tell us that this whole thing is the constant that you would like it to be. So it would tell us that this whole thing, whatever it is, it loses track of everything. It has no idea about lambda anymore. It has no idea about beta anymore. It has no idea about anything anymore. Which is kind of weird because you can take this theory over here and you can repeat all of those steps over there. And you find lambda dependence, you find beta dependence. So what's going wrong with this argument of Susi localization here is that what happens in the argument that leads me to this implication over here is that I'm ignoring boundary effects. So in other words, what's the punchline of this theory is that I have this gravitational path integral of like this Encoded 2 extension of time-like Liouville theory. And Susi localization tells us it does localize. It does localize onto boundary effects. So, and I think what's the work which we're still trying to investigate here is what are those boundary effects that it localizes on, and does this for some weird reason localize onto some points, or what is happening here? So where does this theory localize? But in any case, I think the supersymmetric localization here gave us a strong machinery to study localization. And by maybe even combining like the SUSY localization with just a brute force approach from the gravitational path integral point of view, what can we learn on why does time-like Liouville theory localize? And let me also just highlight this. We have no microscopic theory for time-like Liouville theory. So whereas like we have a very good understanding of like space-like Liouville theory, and we know that the microscopic theory associated with it is like a matrix model, we have no idea about time-like Liouville theory. We have no idea what's the microscopic dual to time-like Liouville theory. And one of the hopes also, of course, in exploring all of this is like to find this microscopic model, because in principle, it could be a microscopic model for a two-dimensional de Sitter space. And it could teach us something about this microstates, this 10 to the 10 to the 120 microstates. And another thing, of course, that you might have realized here, I had a path integral that localized. So I had a path integral that had like this infinite number of degrees of freedom, and it localized onto something very finite. So this is like another, like something that another lore about de Sitter that we hear a lot is like that the Hilbert space of de Sitter space is like finite dimensional. So the big question that I think also arises here, not just in this time-like Liouville theory over here, but also in the supersymmetric extension, is whether like this localization is like some hint of the Euclidean path integral of this finiteness that we associate to de Sitter space. And so with this, I'm basically at the end of my talk. So the one punchline that I wanted to give you in this talk is really that I think there's a lot of things that we can do in two-dimensional de Sitter space. And I think the two-dimensional de Sitter space can be a setup which we can really explore from this microscopic perspective, maybe even. And these are just like two big questions that I still have and that I want to understand. And in particular, I think like understanding the supersymmetric extension of Liouville theory, it could just be a model where we can understand like higher genera, localization, and so on and so forth. So I think it has a lot of, how do you say, open questions that we can follow up and try to understand. That's about it. Thank you.
Thanks. Are there further questions for Beatrix? Yes.
So you mentioned that the motivation to introduce supersymmetry is to cure the UV divergence in higher genus surfaces. Can you explain a little bit why you respect that?
I mean, right, on higher gen, I mean, we haven't, I mean, it's one of the motivations that we haven't explored yet in detail. I think for me, the point is that, I mean, on higher, like in general, what we compute is like the index, right? So, and so you have some cancellations there. So, I mean, it's you have to understand, you have to explore it in more detail for me to give you like
I would naive expect that you need to introduce supersymmetry in the matter CFT.
Oh yeah, sure. No, but we need the supersymmetric matter theory. Yes, of course.
Okay, thank you.
Oh no, of course, but the matter theory has to be supersymmetric. Yes. And so then there are cancellations, or there can be cancellations.
Do you understand how to recover the duality B over 1 over B perturbatively?
Oh.
Perturbatively.
I mean, which one do you mean now? Like this is, I have not emphasized this. That's actually a very important point about n equal to 2 supersymmetric Liouville theory. I completely stripped this under the carpet. So you see that I wrote down 1 over beta here only, whereas like over there I wrote Q, and then I should have said this here. So similar, I have that Q is equal to beta inverse minus beta. Whereas for the supersymmetric version, Q is only 1 over beta. So there's no quantum correction basically. In n equal to 2 Liouville theory, I have no beta going to 1 over beta symmetry. It's lost.
And in the time-like Liouville.
Yeah.
there is the duality, right? The
Yeah.
time. And how do you recover it perturbatively?
Oh, it's lost. That's interesting.
Lost.
That's another very interesting point. The sphere partition function does not have this this symmetry, b going to 1 over beta anymore. There has been a recent paper actually that also tried to understand this by Jiribe and someone else. And basically, I think what they have tried to argue is that it's lost because you can derive this using some column gas approach. And there it's kind of in this machine or in this setup, it's lost. So but it's a very curious point actually that this whole theory was symmetric under b going to 1 over b, and then the sphere partition function just loses track of it. So it has no idea anymore.